Imagine a city, perfectly ordered but completely invisible. Today, we're diving into the atomic scale world inside crystals, and we're going to look at the incredible roadmaps scientists use to navigate a place they can't even see.
So that's the million-dollar question, isn't it? When you can't see the streets, how in the world do you draw a map? Well, it turns out the key is to use something that can interact with this invisible city, a beam of electrons. By watching how those electrons scatter, scientists can actually create a super detailed map. Let's start with the first type they discovered.
All right, our first navigation tool is something called Kikuchi Lines. You can think of these as the main highways, the major roads that cut right through the crystal's hidden city.
Now, these patterns show up when you're using a transmission electron microscope, or a TM for short. What you're doing is firing a beam of electrons through an incredibly thin slice of a material. As those electrons zip through, they bump into the crystal's atoms and scatter. And that creates these beautiful, sharp lines. And the crucial part, these lines aren't random at all. They are a direct map of the crystal's internal atomic grid.
I absolutely love this quote because it just nails it. For a scientist who is, for all intents and purposes, lost inside a crystal, these lines are like a compass and a GPS all rolled into one. They provide a clear, unambiguous map to figure out their exact orientation.
So what makes them such a great map? Well, for one, unlike other signals that kind of flicker in and out of view, these bands are incredibly stable. They clearly mark all the major intersections of the crystal's atomic planes, scientists call these poles, and they give you a reliable path to get from one to the next. It's like having a roadmap where the highways are just always lit up for you.
Okay, so Kikuchi lines appear in a TEM, where electrons pass through the sample. But there's another major type of electron microscope, the scanning electron microscope, or SEM. Here, the beam scans the surface of a thick sample, and we look at the electrons that get kicked up from that surface. In this process, it reveals a totally different yet weirdly familiar pattern.
And this brings us to our second phenomenon, electron channeling. If Kikuchi lines are the map from inside the city, this is the map you get by looking at it from the surface.
These are called electron channeling patterns, or ECPs. They're basically these bands of light and dark that show up in SEM images. And here's a fantastic piece of trivia for you. The very first image ever produced by a scanning electron microscope was of this exact effect. How cool is that?
So how does this work? It's a really fascinating process. As the electron beam scans the crystal, whenever it lines up just right with one of the atomic planes, something cool happens. Instead of bouncing back up, the electrons channel deeper into the material, kind of like a bowling ball hitting the lane perfectly. And because fewer electrons escape to be seen by the detector, that spot appears darker, creating a really distinct band on the image.
Okay, so let's just recap for a second. We've got Kikuchi lines in one microscope, and they're formed by electrons going through the sample. And then we have channeling patterns in a completely different microscope, formed by electrons getting kicked up from the surface. They seem like totally separate things, right?
And that leads us to the crucial question. You've got two different machines operating on two different principles, one looking through a sample and one looking at its surface. But if you look at the maps they produce, are they really all that different?
Well, the answer is just incredible. Despite everything being different, the microscope, the mechanism, the patterns are fundamentally linked. They are both drawing a map of the exact same hidden geometry.
This quote here just says it perfectly. Even though the ink is different, one's made from electrons scattering through, the other from a lack of electrons bouncing up, the drawing they create is identical. The roadmap is the same.
So what does this all mean? It means they're two sides of the same coin. Both of these patterns are maps of the exact same crystal city. They're governed by the same rules of physics, and they reveal the same internal structure. One is the view from inside the city, the other is the view from the surface, but they are both, without a doubt, mapping the same place.
Now, this connection isn't just some neat piece of physics trivia. It has some very real-world implications for how we study and even create new materials. So let's get into why this all matters.
You see, for a long time, using electron channeling patterns has been, well, tricky. They are incredibly sensitive. Even a tiny, invisible layer of damage from just polishing the sample can completely wipe out the pattern. The same goes for any coatings you might add to the material, which you often have to do.
But, and this is a big but, here's where things get exciting. Thanks to modern microscopes and new ways of making materials,
These ECPs are making a huge comeback. The key is to look at surfaces that are perfectly, absolutely pristine and undamaged, which we're getting better and better at creating. And this is happening in some really cutting-edge fields. We're talking about materials with perfectly cleaved surfaces, or new materials that literally build themselves one atom at a time. On these perfect surfaces, and with modern microscopes that can pick up even the faintest contrast, electron channeling is becoming an incredibly powerful tool all over again.
And this leaves us with a pretty fascinating thought. The ability to read these roadmaps has basically been there all along, just waiting for our technology to catch up. As our microscopes get more and more powerful, you just have to wonder, what revolutionary new materials, what undiscovered atomic cities are out there right now just waiting for us to finally see the map?